Hi, good afternoon everyone. My name is Yuheng Liu, and I'm a second-year PhD student at UC Irvine, supervised by Professor Xiaohui Xie. Today, I'm excited to present OmniRoam, our framework for wandering through virtual worlds by generating long, immersive panoramic videos. This is joint work from my internship at Adobe Research, together with our wonderful collaborators. What you are seeing here starts from a single panoramic image or a short video, plus a camera path that you specify. From that, OmniRoam generates a long high-resolution panoramic video that lets you wander freely through the whole scene. And because every frame is a full panorama, capturing everything around you at once, the world stays coherent as you move, even as the camera travels far and loops back to where it begins. But making the hold up over a long trajectory is a real challenge. It really comes down to consistency. We need the world to stay coherent in space as you look around, and stable over time. So what you see earlier is still there when you come back. Over hundreds of frames, small errors build up and the world starts to drift. And that's exactly where existing methods run into trouble. Broadly, those methods fall into two camps. The first work in the perspective domain. Approaches like Imagine 360 lift a perspective video into a panorama. This can look sharp on any single view, but since each frame only sees a slice of the world, they lose the global structure once the camera moves widely. The second camp generates panorama directly, with camera control. The catch is that these methods are mostly trained and tested on short clips. So when you push them out to long trajectories, error builds up and the scene degrades. Our approach is a global to local design. Generating a long, high-resolution video in one shot is both unstable and far too expensive. So instead, we split the problem in two. First, a fast, low-resolution preview lays down the global structure of the whole journey. Then a refinement stage fills in the local detail. Let's walk through the preview stage. It has two inputs, your visual input and the camera trajectory. The visual input first passes through an encoder into a latent. We concatenated that latent frame by frame with the video we are generating. The second input is the trajectory. Our idea is not fit in the raw trajectory, but to decompose it into two independent parts, flow and scale. Flow is the preferred direction, where the camera is heading at each moment. It passes through a small MLP to become preferred directional condition. Scale is a single global number, how far the camera moves at each step, and which sets the playback speed. We project it, and then copy it across all frames, so it controls the whole sequence uniformly. This decomposition keeps control simple and intuitive. Flow sets the direction, scale sets the speed. And because scale is a single globe knob, turning it up lets a short preview cover very long trajectory. Finally, both the visual and the trajectory tokens serve as the conditions to our preview model, which then generates the preview video. Now, let's follow the refine stage. We start from the preview video and pass it through the encoder into a latent. The preview is produced at an accelerated scale, and we want the final video at a target scale, which is normal playback speed. From these two scales, we first compute a visibility mask. This mask decides how the preview is divided into segments. And for each segment, it marks a small window of the frames from the preview to keep visible as conditioning. We then apply the scale alignment, multiplying this mask with the latent. So each segment ends up conditioned on just its own sparse slice of the preview. Each segment goes into our refined model, and we generate at a higher spatial and temporal resolution. Because every segment is anchored back to the same preview, they all stay consistent with the global structure. Finally, we stitch the refined segments together, letting neighboring ones share few overlapping frames so the transition stays smooth, and that gave us the final refined video. Beyond these two stages, the framework extends naturally in two directions. The first is a real-time preview. By distilling the preview model into a lightweight version, we can generate an 81-frame panorama in about 7 seconds, instead of several minutes. That's fast enough to explore interactively. The second comes almost for free, because the long videos stay coherent across views. We can feed them straight into 3D Gaussian splatting and reconstruct an explorable 3D scene from a generated wandering video. To train for this, we need data with accurate trajectories, and here we make one key choice. In a panorama, rotating the camera reveals nothing new. It just shifts the image sideways, like scrolling. So instead of the usual 6 degrees of freedom, we drop rotation entirely and define every trajectory purely by translation, by where the camera actually moves through the space. And this keeps the control space clean and lets the model focus on real motion. We then build a hybrid dataset. It has around 2,000 real-handled panoramic videos across diverse indoor and outdoor scenes. And it is 1,000 synthetic scenes rendered from 3D Gaussian splatting with precise, physically plausible trajectories. Finally, to measure long-term consistency, which standard video matrix means, we introduce a new metric called loop consistency. The idea is simple. We send the camera on a closed loop and check whether it returns to where it starts. If the scene is truly consistent, the last frames should match the first. Now, let's look at what OmniRoam actually generates. Let's start with the preview stage. From a single input, we generate previews under a range of different camera trajectories, like moving forward, following an S-curve, and so on. In each case, the model stays faithfully to the path you specify, and quickly sketches out where the camera would go through the scene. Next is the refine stage. Here, we take one of these previews and turn it into the final result. The resolution goes up. The accelerated preview is expanded back to normal speed. And the short overview becomes a long, continuous video. As the camera keeps moving, the structure stays consistent from start to finish. Now, the loop consistency comparison, which is where the difference really shows. Here we compare our full method against two alternatives. An autoregressive version that builds the video segment by segment, and the perspective version that drops the panorama representation. For our method, when the loop closes, the final view lines up almost perfectly with where we begin, and the scene stays consistent the whole way around. The autoregressive version gradually drifts as the camera moves, and by the time the loop closes, it loses track of the original scene. The perspective version doesn't recover either, losing geometry and fine detail along the way. Together, this tells us that both the panoramic representation and the global to local design are essential to staying consistent over a full loop. On the numbers, our method outperforms prior work across visual quality, trajectory accuracy, and loop consistency at both resolutions. To wrap up, OmniRoam is a global to local, preview and refine framework for long horizon panoramic wandering. Our contributions are the two-stage design, a large panoramic video dataset with accurate trajectories, and the loop consistency metric. Together, they enable coherent, controllable exploration of large things. And that brings us to the end. If you'd like to dig deeper, you can scan the QR code on this slide for our paper, code, and the results. And if you have more questions, please come find us at our post session. Thank you for listening.